Hello, it's Stat135, lecture 25. Today's a special lecture on moment generating functions of x. This is not covered in the book. Next time we'll be finishing section 4.5 and start section 4.6. So the moment generating function of x. Let's talk what the kth moment of a random variable is. It's just the expectation of x to the k for k 0, 1, 2, 3, and so on. So, for example, the first moment is the mean, the second moment is the first and second moment together give you the variance, and so on. Basically, moments give you information about your random variable, and in fact, all the moments uniquely specify the distribution of x, but we'll talk about that a little bit next time. So computing the moments of a random variable is sometimes hard because it involves computing complicated integrals or sums, right? Just take a look at what the definition of the expectation is in terms of a integral or a sum. But the moment generating function allows one to compute the moments by computing derivatives, which is easier. So let's begin with a review of the Taylor series of an exponential. And in fact, for t in a real number and x a random variable, you can also do the Taylor series for e to the tx, and you can take derivatives on both sides and evaluate these derivatives at 0, and you'll see that the kth derivative of e to the tx evaluated at t is 0 is just x to the k. Now, that should motivate how we should define a moment generating function. We want the moment generating function to give us information about the kth moment. So if I take the exponential, if I take the expectation of both sides of this formula right here, then and suppose that I take the derivative outside of the expectation. If I can just pass that derivative outside the expectation, then I would get that my moment generating function should be the expectation of e to the tx, and that the kth derivative of the expectation of e to the tx evaluated at t is 0 would be the expectation of x to the k, which is exactly what I want. So let's that's just motivation. Let's recall the formula for the expectation of a function of x, and we'll define the moment generating function to be the expectation of e to the tx. So here e to the tx is just a function of x, so it's g of x in this case. And I've just written out what that means in terms of expectation for discrete and continuous random variables. Just a heads up that in the homework, actually, for some reason, I write, instead of m of x, I write m sub x, I write phi of x. So just be aware of that, but no big deal. And so then the kth derivative of the moment generating function evaluated at t is 0. So here's what that means in terms of the definition of the moment generating function. And then it seems like I'm just passing the derivative through the expectation. And let's not worry about why this is justified. You need to know some things from real analysis, such as the dominated convergence theorem, the mean value theorem, for me to explain this. But anyone with that background that'd like to talk about it, just let me know. So anyway, once we have this, then we know that the kth derivative of e to the tx evaluated at t is 0 is x to the k. So here we have it, that the kth derivative of the moment generating function is the kth moment. So a moment generating function doesn't always exist in an interval around 0. I've provided an example for you at the end of these lecture notes for those of you that are interested in that. But let's take a look at some examples. So we did x Bernoulli p. So x just takes two values, 1 and 0. X is 1 with probability p. X is 0 with probability 1 minus p. So I asked you to find the moment generating function as well as the expectation of x and the variance of x. And you did a great job with that. You can see here that the moment generating function is 1 plus p times e to the t minus 1. And that's well defined for all t. Then to find then we find the first and second moment by taking the first and second derivative of the moment generating function and then setting that equal to 0. And then the variance is a function of the second moment minus the first moment squared. So we get the usual formulas for expectation and variance of Bernoulli p. Then we did a more complicated example where x is a gamma r lambda, and so we found the moment generating function for gamma, and so first we write out the definition, and then we pull out the constants. Remember that the variable here is x. Now notice that this integral will converge for t minus lambda less than 0 because it's essentially a gamma, so you know that this is going to converge. But when t minus lambda is positive, there's no way this is going to converge, because just think about the shape of the function here. The area under this shape, there's no way that's going to be finite. So to solve this integral, we do a u substitution with u is equal to minus t minus lambda times x, where minus t minus lambda is a positive number, so it doesn't change the, we're still then now integrating from 0 to infinity. And I just make my substitutions here, pretty straightforward. And then at the next line here, we see the gamma function of r rearing its head. Once we recognize that as the gamma function of r, we have a beautiful cancellation of gamma functions in the numerator and denominator, giving us our moment generating function. And this is valid only for t less than lambda. So what makes the moment generating function so helpful is the following theorem. If a moment generating function exists in an interval around 0, then the kth derivative, I've already written that. So the kth derivative of the moment generating function evaluated at t is 0 is the kth moment. And the reason that we need it to be the moment generating function to be defined on an interval containing 0 is because I'm taking the derivative at 0. So for there to be a dx containing 0, the moment generating function has to be defined not only at 0 but around 0. So then I asked you to find the expectation and variance of the gamma. So you found the first and second derivative of the gamma function. This was a pretty straightforward calculation. I won't go over this. And then you plug in 0 for t. So we got the usual values for the expectation and variance. And then I asked you guys to compute the moment generating function for a geometric 1/3. And so we recalled the probability formula for geometric 1/3. And so here the moment generating function is an infinite sum. And so it's only going to converge. It's only going to converge for some limited t here. And I'll let you read this, but essentially the restriction on t is that e to the t times 2/3 has to be less than 1, or equivalently t is less than the log of 3/2. And then we get our moment generating function, which is well defined for t less than log 3/2. So anyway, that's the show. Hope you enjoyed the moment generating function. We'll just summarize next time about this, and have a great weekend. Bye-bye.